In this problem, we'll consider the series expansion solution of this non-homogeneous differential equation, y double prime plus y is equal to 1 over x. And we're going to solve this as a series about x equals 1. Obviously, you can't do this as a series about x equals 0 because 1 over 0 is undefined. So we'll find this as an expansion about x equals 1. We're also given the initial conditions that y of 1 is equal to 0 and also that y prime of 1 is equal to 0. Okay, now to do this, first let's deal with the left-hand side. We'll deal with the right-hand side shortly. So y of x is equal to summation n equals 0 to infinity a sub n times x minus 1 to the n. That's a series expansion about 1 as opposed to a series expansion about 0. Now if I take two derivatives, I will get summation n equals 0 to infinity of n times n minus 1 a sub n times x minus 1 to the n minus 2. Taking two derivatives and applying the chain rule multiplies by 1, so I don't have any issues with that. Now I apply the usual technique that this is summation n equals 2 to infinity of n times n minus 1 a sub n times x minus 1 to the n minus 2. And then I'll shift the index so that I get n equals 0, 0 to infinity of n plus 2, n plus 1, a sub n plus 2 times x minus 1 to the n. Okay, so that's going to give me the y prime and the y terms. So that means that y double prime plus y will be equal to summation n equals 0 to infinity of n plus 2 times n plus 1 times a sub n plus 2 plus a sub n times x minus 1 to the n. So that is the left-hand side. The right-hand side is a bit more interesting because now I don't have a 0 here, I've got something else. So 1 over x, we need to write this as some kind of expansion about x minus 1. And there's a big hint in the problem here that 1 over x is equal to 1 over 1 minus negative x minus 1. Okay, before I go over why I did this, let's go over that it actually works. That if I take negative negative x, that becomes plus x. Then if I have three minuses, minus minus minus, I get 1 minus 1, and those cancel. Now, why in the world would I do that? The reason I do this is because we have the standard expansion that 1 over 1 minus t is equal to 1 plus t squared plus t the third, or summation n equals 0 to infinity t to the n. And this works as long as absolute value of t is less than 1. So, by the exact same logic, everywhere I see a t, I'll replace by negative quantity x minus 1. And I get summation n equals 0 to infinity of negative x minus 1 to the nth power. Or summation n equals 0 to infinity of negative 1 to the n times x minus 1 to the nth power. And this is going to work as long as absolute value of x minus 1 is less than 1. So therefore, by the principle of matching the series, if this is equal to this, that means that this thing in brackets has to be equal to the coefficient here, negative 1 to the n. So this sets me up the recurrence relationship that n plus 2 times n plus 1 a sub n plus 2 plus a sub n has to be equal to negative 1 to the nth power. Solving for a sub n plus 1, we get a sub n plus 2 is equal to negative 1 to the n minus a sub n all over n plus 2 times n plus 1. And let me write this in terms of a sub n. So everywhere I see an n, I'll replace by n minus 2. I get negative 1 to the n minus 2 minus a sub n minus 2 over n times n minus 1. And so this is going to be the recurrence relationship that I'll use in order to find the coefficients. So to build this with Excel, So column A, column B, rows 1, 2, 3, 4, 5, and so on. So I'll put a 0 here, and then a sub 1 plus 1 and fill down. So that's going to be 1, 2, 3, 4, 5 for my values of n. If I come back to my original differential equation, I see that y sub 1 is equal to 0. That's a fancy way of saying that a sub 0 is equal to 0. Also, a sub 1 is equal to 0. And so those are given to us right away from the initial values. After that, we use this relationship. So this is going to be equal to negative 1 to the n minus 2. So let me just go back 2 steps, a1, minus the term that's 2 back in the sequence, so that's 2 back here, divided by n, which is this number here, times n minus 1, which will be this number here, a2. Then if I fill that down, that will give me the first few terms in the power series expansion. Okay, now the problem then asks us to actually figure out all terms up to x the fourth by hand. So we have a sub 0 was equal to 0, a sub 1 is equal to 0, a sub 2 will be equal to negative 1 to the 0 minus a sub 0 all over 2 times 1. So that's equal to 1 minus 0 over 2, which is a half. A sub 3 is equal to negative 1 to the first minus a sub 1 over 3 times 2. So negative 1 minus 0 over 6 for negative a sixth. And finally, a sub 4 was equal to negative 1 squared minus a sub 2 over 4 times 3. So that's going to be 1 minus 1 half all over 12, and that's 1 over 24. And so the power series expansion is going to start like this. It's going to be 0 plus 0x minus 1 plus a half times x minus 1 squared minus a sixth times x minus 1 to the third plus 1 over 24, x minus 1 to the fourth. And if I keep adding up, I can approximate the solution y to as much accuracy as I wish by just taking enough terms. So that is the expansion for this one, and this is going to converge for absolute value of x minus 1 less than 1.